In this video, we're going to talk a little bit more about probability, specifically probability models, compound events, and complements of events. A probability model is merely a way that we express the chances of something happening. So there's a couple vocabulary terms that we use when we talk about probability. The first being sample space. So that is the list of all the possible outcomes or results that could happen given an experiment. Within that sample space or a list or a set of numbers or outcomes is something that we call an event. So that is, like I said, a subset of that sample space. So those are the things that could happen within that sample space. Sometimes it's all of the sample space, sometimes it's none of it, sometimes it's just a few pieces of it. And then we define this probability with a capital P, and then in parentheses we describe the event that's happening. And then that is going to be a ratio, which ends up being a decimal between 0 and 1, and that is the number of outcomes in an event, so how often that's going to happen, out of all the possible outcomes or our sample space. Also, something to remind you of is this union and intersection, because we're going to be talking about compound events in just a moment. So remember, union is the thing that looks like a U, really nice and easy to remember. That means or. Anything that happens in A or B, which is usually a combination of all the things. And then there's also intersection, which means and. So we denote that by this like upside down U. And that's, if I was drawing a Venn diagram, the intersection of both A and B, which would result in only this part and not that or that part. In probability, when two events happen at the same time, we call that a compound event. So you can either have a mutually exclusive compound event or a not mutually exclusive compound event. So essentially, if something is mutually exclusive, these two events agree to exclude each other's elements, which that means is that if I have probability of A happening and probability of B happening and they share nothing in common, their sample spaces have 0 things in common, that's what we call mutually exclusive. They exclude each other, but they're still together, mutual exclusion. So the way that we express that is with this P, with A or B, whatever those events are. You could always use the union symbol here. All you do is you add up the probability of A happening and the probability of B happening, and there you go, there's your probability. If they are not mutually exclusive, if they share even one thing in their sample spaces together, we call that not mutually exclusive. So the only thing that differs between here and here is that when you add the probability of A and the probability of B, you have to then subtract the probability of A and B, or the intersection. And that's because they're not mutually exclusive because they have something in common, or their intersection. So let's walk through some examples. This first one says that a pair of dice is rolled, and it's asking us what's the probability that the sum of the numbers that is rolled is either a 7 or an 11. First thing we got to talk about is the combination of two dice that are rolled. So if you don't know, a die has 6 sides. So if I'm rolling 2, I can have a sum of anywhere between 2 and 12. So let's look at that. Here's a list of all the possible combinations when I roll 2 dice. Keep in mind that when you roll 2 dice, 1 and 5 is different than 5 and 1, because although the dice may look the same and they may result in the same number, they're actually 2 different things being rolled. So a 1 may look the same on both of them, but I have to take each die into account and count them separately. So what I'm going to first do is look for how to make a 7, and that is made with 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, and 1 and 6. So the probability of rolling a 7 is 6 out of 36. And the probability of rolling an 11 is 6 and 5, and 5 and 6. So that's 2 out of 36. Next, I need to think about if this is going to be mutually exclusive or not. So I'm going to look at my sample space and what I've chosen as far as the events of rolling a 7 and rolling an 11. So what's in blue and what's in red, they don't have any overlap. So although these two things are being compared together and they share a sample space, they are mutually exclusive because these two groups have nothing in common. So because it's mutually exclusive, all I do is add up the probability of 7 and the probability of 11. And when I put those two things together, I get a mutually exclusive probability of rolling a 7 or an 11 as 8 out of 36 or 2/9. So let's say I roll the same pair of dice. Let's find the probability that the sum of the numbers that's rolled is even or a multiple of 3. So let's break out that list of sums from 2 dice being rolled. All right, here we go. So let's find the probability of rolling an even sum. So this is going to be even, that's 2, 4, so all my 4s, my 6s. This is a nice pattern on a diagonal. This next one is 7, so 8, then 10, and 12. So the odds of rolling an even sum is 18 out of 36, or 1/2. So let's next find the probability of rolling a multiple of 3. So that's going to be 3, 6, 9, and 12. So there are 12 of those out of 36, or 1/3. So now I need to consider if this is mutually exclusive or not. And because there's an overlap between what's blue and what's red, this is not mutually exclusive. Remember, they share a sample space, and there's going to be an intersection between even and multiples of 3. So that means I use the same equation, except I need to subtract the probability of even and a multiple of 3. So there are 6 of those highlighted in purple, and that's 1/6. So when I combine all of these, I get probability of the even, add it to the probability of rolling the multiple of 3, and then you subtract their intersection, which I can use that symbol for if I prefer. And I'm going to get 24 over 36, or 2/3. Something else in probability that's useful is the complement of an event. So for every sample space that you have these events which are subsets. So for every event, the thing that doesn't happen, that's also in the sample space, is called the complement. So an example is, let's say you flip a coin and it gets heads. The complement of that is a tail. If you draw a black card out of a deck, the complement is a red card. So essentially, if you find the probability for an event happening, like probability of A, in order to find the complement, you take 1 and you subtract that probability. Something else to note is that sometimes it's denoted with this little mark up here, or there's a bar up top. Either will work. So let's put the complement to use. Let's say in a random group of 10 people, let's find the probability that 2 people will have the same birthday, month and day, year not included, and let's say it's for a typical non-leap year. So if we define the number of people in the sample space, and the way that we would write that is we would say little n parentheses big S for the sample space. It's going to be 365 to the 10th power, because there are 10 people, there are 365 days in a year, so that's all the possible birthdays that could exist. Lots of birthdays. So if I want to find the probability of 2 people having the same birthday, that's so much work. So what I'm going to actually do is I'm going to find the probability that 2 people won't have the same birthday. So I'm actually going to define that as the probability of this event not happening, so the complement. So what could happen is that there are 365 possible birthdays for the first person. And if the next person does not have the same birthday, I have one less thing to pick from, all the way up to 356, because there's 10 people. And I'm going to divide that by this number, 365 to the 10th, because that's my sample space. So the probability of those 2 people not having the same birthday is about 88%. So in order to find the probability that people will have the same birthday, I'm going to do 1 minus the complement, so that's 1 minus 0.883. So the probability of a random group of 10 people having the same birthday is about 11.7%, or 0.117. So this problem is actually a famous problem. It's called the birthday problem or the birthday paradox. And here's a graph that shows pretty interestingly what happens when you increase the number of people in a given sample and the probability that they'll have the same birthday. So the red line is that they will have the same birthday, and the blue line is when they will not. So this one is our complement, and this one is our actual event. And that's going to do it for this video. Thanks for watching.